Hello, and welcome to Groups 14 video presentation for CHBE 346. My name is Cindy, and I'm here with my partners Abdul, Hejin, Hansdeep, and Sina. This video is going to be about a gas turbine, specifically jet engines principle with its application. There are several sections that we will cover in this video. I myself will cover the general step of a combustion engines and compare them with the jet engine steps. Hejin will cover the in-depth of the fourth step of the gas turbine. Abdul will cover the Brayton cycle and how to improve the efficiency of the gas turbine. Sina will cover the 4 different types of gas turbines, how each type is operated, and the application for each of them. And lastly, Hansdeep will cover the thermodynamics principle behind jet engines. So you might ask, what is a gas turbine? A gas turbine is an internal combustion engine that uses air as the working fluid. The engine extracts chemical energy from fuel or air and converts it to mechanical energy using a gaseous energy such as flammable gas. That gas will drive the engine that turns the propeller for the airplane. There are 4 basic steps for internal combustion engine. Number 1, the intake of air. Number 2, the compression of the air. Number 3, the combustion of the air, where the fuel is injected and burned to convert the stir energy. And the 4th one, the expansion and exhaust, where the energy is used. In turbine engine, however, the same 4 steps are similarly the same, but in different places. Number 1, the inlet section is where the air is sucked in for the compression to begin. Number 2, the compressor section, where it supplies the large mass of air and squeezes the air to high pressure. Combustion section, where it converts the mechanical energy from turbine to gas energy. And the 4th one, the turbine or the exhaust section, is where the output shaft of the power to drive the propeller. Now I will hand this to Hejin for the next section.
Thank you, Cindy. Let me explain more details of what happens in each part of the gas turbine. In the first inlet section, clean and unrestricted airflow comes in. Second part of gas turbine is compressor section. The compressor must supply all the air in an efficient manner at high static pressures. In an axial flow compressor, which is primarily used in industry, each stage boosts the pressure from the previous stage. A single stage of compression consists of a set of rotor blades attached to a rotating disc, followed by stator vanes attached to a stationary ring. Generally, the compressor rotor blades convert mechanical energy into gaseous energy. The stator vanes slow the air by means of their divergent duct stage, converting the accelerated pressure to higher static pressure, and this process is repeated. The air then enters the diffuser section of the engine, which is a very divergent duct. Once the air flows through the diffuser, it enters the combustion section, also called the combustor. In this part, large amounts of fuel and air is burned and released as heat. Then, the turbine converts the gaseous energy into mechanical energy by expanding the hot, high-pressure gases to a lower temperature and pressure. After the gas has passed through the turbine, it is discharged through the exhaust. Though most of the gaseous energy is converted to mechanical energy by the turbine, significant amount of power remains in the exhaust gas. This figure is for the jet engine components and corresponding thermodynamic states. The inlet and the compressor sections are included in the function A to B. The combustion section is on the line B to C. The turbine section starts from C to D. And these go back to the first point A. And the next one will be covered by Abdul.
Thank you, Hejin. Now I'll talk about the Brayton cycle. The Brayton cycle is a thermodynamic cycle that describes the working of a constant pressure heat engine. Brayton cycle can be used to explain all the steps that take place in the gas turbine. The first step involves adiabatic compression. From the pressure volume graph and from the temperature entropy graph, we can see that There is an increase in pressure and temperature while the entropy stays the same. This step takes place at the inlet and compression part of the turbine. The second step involves constant pressure combustion. The pressure does not change, but there is an increase in both entropy and volume. Next step is adiabatic expansion. The volume increases, temperature and pressures goes down, but the entropy stays the same. The expansion here is used to turn the turbine and generate work. The last step just involves cooling of air back to its initial condition at constant pressure. But how do we calculate this efficiency? The efficiency can be calculated using both temperature and pressure at different stages of the cycle. The formula displayed can be used to find the effectiveness of the Brayton cycle. However, the derivation for these formulas would not be explained in this video. So the question now is, can the efficiency and the power of the turbine be improved? The answer to that is yes. There are two ways to increase the efficiency of the Brayton engine or Brayton cycle. The first way is by increasing the pressure ratio. As seen in figure 1 above, increasing the pressure ratio increases the efficiency of the Brayton cycle. So why not keep increasing this ratio? There are practical limits when it comes to increasing the pressure ratio. First of all, increasing the pressure ratio increases the compressor discharge temperature. This can cause the temperature of the gases leaving the combustor to exceed the metallurgical limits of the turbine. Also, the diameter of the compressor blade becomes progressively smaller in higher pressure stages of the compressor. Because the gap between the blades and the engine casing increases in size as the percentage of the compressor blade's height, as the blade gets smaller in diameter, the greater percentage of the compressed air can leak back past the blades in higher pressure stages. This causes a drop in compressor efficiency and is most likely to occur in smaller turbines. The second way to improve efficiency is by adding recuperator. A recuperator is the heat exchanger that acts as a counterflow energy recovery device positioned within the supply and exhaust air streams of an air handling system in order to recover the waste heat. In many processes, heat is generated in the combustion chamber by combustion, and the recuperator helps in reclaiming this heat. Adding a recuperator to the system can increase the overall efficiency of the Brayton cycle. So the next part would now be presented by Sina Adabi.
Thank you, Abdul, for the great information. In this section, we're going to talk about different types of gas turbines. These are turbojet, turbofan, turboprop, and afterburning turbojet. All these gas turbines share some common parts in their engines: combustion sector, compressor, turbine, an inlet, and a nozzle. Turbojet. Large amounts of surrounding air are continuously brought into the engine inlet. At the rear of the inlet, the air enters the compressor. We have to supply energy to turn the compressor. At the exit of the compressor, the air is at a much higher pressure than free stream. In the burner, a small amount of fuel is combined with the air and ignited. Leaving the burner, the hot exhaust is passed through the turbine. The turbine works like a windmill. Instead of needing energy to turn the blades to make the air flow, the turbine extracts energy from a flow of gas by making the blades spin in the flow. Turbofan. The incoming air is captured by the engine inlet. Some of the incoming air passes through the fan and continues on into the core compressor and then the burner, where it is mixed with fuel and combustion occurs. The hot exhaust passes through the core and fan turbines and then out the nozzle. As in a basic turbojet, the rest of the incoming air passes through the fan and bypasses or goes around the engine. Turboprop. There are two main parts to a turboprop propulsion system: the core engine and the propeller. The core is very similar to a basic turbojet. There may be an additional turbine stage present which is connected to a drive shaft. The drive shaft is connected to a gearbox. The gearbox is then connected to a propeller that produces most of the thrust. The exhaust velocity of a turboprop is low and contributes little thrust because most of the energy of the core exhaust has gone into turning the drive shaft. Afterburning turbojet. Afterburning turbojet is made by adding an afterburner to a core turbojet. The afterburner is used to put back some energy by injecting fuel directly into the hot exhaust. The nozzle of the basic turbojet has been extended and there is now a ring of flame holders in the nozzle. When the afterburner is turned on, additional fuel is injected through the hopes and into the hot exhaust stream of the turbojet. The fuel burns and produces additional thrust, but it doesn't burn as efficiently as it does in combustion section of turbojet. In this section, we're going to talk about different applications of gas turbines. Turbofans are used by most modern airliners because of their high thrust and good fuel efficiency, whereas turboprop is used in low-speed transport aircraft like cargo planes and small commuter aircraft. Afterburning turbojets are only used in supersonic aircraft like fighter planes. The next section will be covered by Hansi.
Thank you very much, Sina. Now I'm going to describe a bit about jet engines, which are a crucial part of the transportation in the modern world. But exactly how do they function, and how do the thermodynamics comply? The motion of an aircraft is due to the air propulsion. As the jet flies, the engine accelerates the air and a thrust is produced, where the mass of air flow rate is multiplied by the difference in exit and inlet velocities of the air. Jet engines, as described before, provide thrust by burning air with the fuel in a combustion chamber and exhausting the high temperature mixture through a nozzle that accelerates the air. Undoubtedly, efficiency is a major topic when it comes to discussing engines. The overall efficiency of jet engines is found as the ratio of the propulsive power to the power obtained by burning fuel. This can be further broken down to the overall efficiency being the product of thermal and propulsive efficiency. Thermal efficiency is the ratio of kinetic energy to the thermal energy of the fuel, while propulsive efficiency is the ratio of propulsive power to the rate of kinetic energy. In these equations below, delta EC represents the kinetic energy of air per unit mass. Here we see a schematic of the simplest jet engine, the ramjet model. This is the simplest because it is without a compressor and a turbine. One of the most important parameters when discussing the thermodynamics of jet engines is the Mach number, which is the ratio of the airspeed relative to the plane compared to the speed of sound, which can be expressed in terms of the dimensional constant epsilon. The thermal efficiency of a simple jet can be expressed in terms of the kinetic energy and thermal energy per unit mass absorbed by air. Thus, it is evident that the efficiency depends only on m, and the plot shows this relationship. For velocities below the speed of sound, the thermal efficiency is less than 20% for a ramjet engine. In order to obtain a higher efficiency for small velocities, a compressor and a turbine can be added either side of the combustion chamber. In such an engine, the compression ratio is of great importance. This is the ratio of pressures exiting and entering the compressor. For such an engine, the thermal efficiency is modified and relates to the compression ratio as well as epsilon, as is shown below. As is seen in the graph for thermal efficiency versus Mach number, an increase in the compression ratio leads to an increase in thermal efficiency. Planes with speeds lower than the speed of sound can actually have efficiencies higher than 40%. Another important parameter in jet engines is the inlet temperature to the turbine, which is represented as T3 in the schematic before. This is the highest temperature reached by the air inside the engine. Using Carnot's theorem for maximum efficiency, we see that the thermal efficiency is restricted by the ratio of the inlet temperature, Ti, and T3. The effects of the Mach number on overall efficiency can be seen in the graphs displayed. An increase in the compression ratio leads to a greater efficiency. Moreover, an increase in the T3 over Ti ratio decreases the efficiency. This graph explains why the Concorde, which actually had a Mach number of 2, had higher efficiencies than commercial aeroplanes. The impact of Mach number on thrust is also shown. For all but the ramjet, thrust decreases with increase in velocity. Thus, it is not possible to maximize the thrust and efficiency at the same time due to the upper bound on the temperature ratio of the T3 and inlet temperature. As such, specific choice of aeroplanes determine the best choice of parameters to focus on, whether it is a military plane requiring thrust or a commercial plane which requires efficiency.
Thank you for watching our video. We hope you enjoy it.